We talk about how to write down the general solution of a system of linear equations and why it works. From Thursday's lecture, you saw examples of systems of linear equations that you would be interested in solving. And I also provided a MATLAB script which you could play with, and I gave the results of the demos in a projection. But we have the general question of, given a linear system of ordinary differential equations, how do we solve it? So I'll just do I'll do a simple example first, not a small example. So the question for the beginning of today's lecture is, we want to solve dx dt equals a times x, where x is in Rn and a is n by m. The reason A has to be a square matrix is, if A were not a square matrix, then A times x would be a different size than x, and it wouldn't make sense to say dx dt equals A times x. Because if x is in Rn, its derivative should be in Rn. So if you're going to have something of the form dx dt equals a matrix times x, this must be a square matrix. And so the question is, how? So I'm going to do two different arguments. So the first argument is is just a basically this works argument. So step one. If lambda is an eigenvalue of A and V is a corresponding eigenvector, then x of t, which is simply e to the lambda t times v, is a solution of dx dt equals a times x. So let's first see if this is true. So I'm just saying that if I have an eigenvalue and an eigenvector, then I can construct something which satisfies this linear system. So I'm going to do this just for a 2-by-2 case so that you don't get confused by vectors or not vectors. So we have V is of the form AB. X of t is e to the lambda t AB, which is a e to the lambda t, b e to the lambda t. So I've just written out in component coordinate form what x of t is. So dx dt is d dt of a e to the lambda t, b e to the lambda t. If I differentiate the first coordinate, does a depend on time? No. E to the lambda t, it depends on time. Are you comfortable differentiating that? Yes, at this point from 188 you need to be comfortable differentiating that. E to the lambda t is the first entry. Lambda b e to the lambda t is the second entry. I can factor out the lambda. I can factor out the e to the lambda t. So this is lambda e to the lambda t times ab. So this is lambda times v. lambda times e to the lambda t times v. So we just figured out that dx dt is equal to lambda e to the lambda t times v. I wanted to do that slowly because people are not always comfortable differentiating vectors. Now, a times x is a times x is right here, e to the lambda t times v. A is a matrix. E to the lambda t, is that a vector or a number? It's a number, so it can come out. So here I have a times v. What is a times v? Is v just any arbitrary vector? Is v an arbitrary vector? It's an eigenvector. That's the important thing. Because if v were an arbitrary vector, I wouldn't be able to write anything here. I would just say, well, what a times v is depends on what v is. But I happen to know that v is an eigenvector. So what does a times v equal? Lambda v. So this is lambda e to the lambda t times v. So I calculated dx dt, and I got lambda times e to the lambda t. And I calculated a times x, and I got lambda e to the lambda t. This shows that x of t, which I have defined to be e to the lambda t times v, is a solution of dx dt equals a times x as long as lambda v is an eigenvalue, eigenvector pair of A. Because I've computed the left-hand side. The left-hand side is lambda e to the lambda t times v. I've computed the right-hand side. The right-hand side is lambda e to the lambda t times v. The left-hand side equals the right-hand side. That means this thing is a solution. So whenever you come up with a solution of a differential equation, you just try to you just check that it's a solution by plugging it into the left-hand side, plugging it into the right-hand side, and asking if the two are equal. Are there questions so far? Okay, so we have found one solution where I'm going to do the argument once where I just sort of give you solutions and show they work, and then I'm going to do the argument in a different way where I explain to you why you might have guessed those solutions. Although it's pretty clear that why you would have guessed it at this point, because taking v to be an eigenvector got rid of the matrix A. Okay, step 2. A linear combination of solutions is a solution. All right, so I claim that if x1 and x2 are both solutions of dx dt equals ax, then so is x of t, which is a linear combination of the two. So I claim if I have two different functions, they don't even have to be different, if I have two vector-valued functions that satisfy this system of linear equations, then any linear combination of them will also satisfy it. So all I need to do is plug this into the left-hand side of the differential equation and plug it into the right-hand side. So step 1, compute dx dt. Step 2, compute a times x. Step 3, if they are equal, we have a solution. All right, so I need to compute dx dt. So dx dt is the time derivative of c1 times x1 of t plus c2 times x2 of t. So if I ask you for the derivative of a sum, if I ask you for d dt of cosine t plus t squared, is that the same thing as d dt of cosine t plus d dt of t squared? Yes. And if I ask you for d dt of 8 times cosine t, is that the same thing as 8 times d dt of cosine t? Yes. Differentiation is a linear operator. It will go right, it plays nice with addition, it plays nice with scalar multiplication. This is equal to c1 dx1 dt plus c2 dx2 dt. All right. Now I need, that was step 1. I computed the derivative. Step 2, I need to compute a times x. Well, that's a times c1 x1 of t plus c2 x2 of t. Matrix multiplication, is it a linear operator? Is it linear? Does it play nice with addition, with scalar multiplication? Yes. So this is going to be c1 a times x1 of t plus c2 times a x2 of t. So I've finished step 2. I computed a times x. Step 3. Is dx dt equal to a times x t? So I would like to know whether the left-hand side, which is this, is equal to the right-hand side, which is this. So I want to know whether c1 times dx1 dt plus c2 times dx2 dt equals c1 times ax1 plus c2 times ax2. Is it, I mean, if I just have arbitrary functions of time, there's no reason for this to be true. But are x1 and x2 arbitrary functions of time? Or do we know something extra about them? They are solutions. So because they are solutions, I know that dx1 dt equals a times x1. x1 of t is a solution. And dx2 dt equals a times x2. These are equal because x2 of t is a solution. So this means that if I have two solutions, any linear combination of them will be a solution. Is there anything magical about two solutions? If I had three solutions, would any linear combination of three solutions be a solution? Yes. 4 solutions, 5 solutions. The only reason I chose 2 solutions was to save chalk, because otherwise we'd have to raise your tuition to buy me more chalk. That's not funny, actually. The only reason I did 2 solutions was so that you would see the computation and not get distracted by big expressions. Any combination of 2 solutions will be a solution. So what do we have? From step 1, we have that if you have an eigenvalue and an eigenvector, then for sure this will be a solution. From step 2, we have that any combination of solutions is a solution. So step 3, we combine steps 1 and 2 if lambda 1 v1, lambda 2 v2, lambda k vk are eigenvalue-eigenvector pairs of A, then x of t, which is a linear combination from this, I'm going to build a solution. From this, I'm going to build a solution. From this, I'm going to build a solution. All the way up to this, I'm going to build a solution. And any linear combination of them will be a solution. So c1 e to the lambda 1t v1 plus c2 e to the lambda 2t times v2 plus ck e to the lambda kt vk is a solution. Okay, so this is what I did on Thursday. I had a 3x3 matrix. I found the, first I had a 2x2 matrix. I found 2 eigenvalues and 2 eigenvectors. That gave me a general solution. I needed the initial data to choose the coefficients. So step 4 is to choose the coefficients using the initial data. So step 4, use the initial condition to pin down to determine the coefficients. So normally you have 2 things. First of all, you might have the problem you might have the system of linear equations. So this would come from whatever it is that you're trying to model. If you're trying to model coffee particles flowing through a suite of rooms, that would be what determines these coefficients, this coefficient matrix. But there are 2 things that you need to get a specific solution. You need to know what you're modeling, and you need to know something like the initial coffee distribution at time 0. So the initial coffee distribution at time 0 would be some vector in Rn. So in our case, the initial distribution was 100 milligrams in the first room, 0, 0, 0, 0 in all of the other rooms. But there could have been a different initial distribution. There could have been some other housemate who was also making coffee. So it's this thing which is going to determine those coefficients. So you plug t equals 0 into the solution. And we get that x at time 0 x at time 0, if I plug t equals 0 in, all of those exponentials become 1. I have c1 v1 plus c2 v2 plus ck vk. And I would like that to equal my initial data. Which is some vector in Rn. So here you have to wonder for a little bit. These are eigenvectors. And this is some arbitrary vector in Rn. If I'm going to be able to satisfy every possible initial data, if I want my solution to work no matter what the initial data is, if I'm in R3, would it be enough to have only 2 eigenvectors to build every possible initial data in R3? No. If I were in R5, would it be enough to have 4 eigenvectors? No. If I'm going to be able to satisfy this, I need at least n eigenvectors. So this, I need n eigenvectors. Now, is it enough just to say I have n eigenvectors? What if I had the eigenvector 1, 1, 1, the eigenvector 1, 1, 1, the eigenvector 1, 1, 1? Could I build every vector in R3 using the eigenvector 1, 1, 1, 1, 1, 1, 1, 1, 1? No. I need n linearly independent. So this is a theorem. Theorem. If A is an n by n matrix with n linearly independent eigenvectors, then you can solve dx dt equals ax, x at time 0 equals x naught for any x naught in Rn by choosing the coefficients C1 up to Cn correctly in the general solution. X of t is C1 e to the lambda 1 t times V1 plus C2 e to the lambda 2 t times V2 up to Cn e to the lambda n t Vn, where lambda 1 is the eigenvalue corresponding to V1, lambda 2 is the eigenvalue corresponding to V2, lambda n is the eigenvalue corresponding to Vn. And in general, all you have to do to find C is solve this problem, where P is the matrix built out of the eigenvectors. Another way of understanding this theorem is if A is diagonalizable, then all of that follows. So A has n linearly independent eigenvectors is the same thing as A is diagonalizable. Okay, so this was the first argument for where that solution comes from. Now a different argument. Because if you don't like the first argument, maybe you'll like the second argument. Okay, first step. Step 1. The solution of dy dt equals lambda y is y of t equals c e to the lambda t. So if I have not a vector, but just a function, I'm looking for some function y of t, so that dy dt equals lambda times y, then certainly this works. Do you agree? Mm-hmm. So if I differentiate this and put it on the left-hand side, and I take this and I multiply it by lambda and put it on the right-hand side, are they equal? Yes. Step 2. I can easily solve dy dt equals lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3 times y. So how can I see that I can easily solve that? That's asking me to solve. Well, the left-hand side would be, okay, so y of t, vector y of t, is it has a first entry, it has a second entry, it has a third entry. I want to get what this vector, I have a system of differential equations in vector notation. I'm asking that dy1 dt, dy2 dt, dy3 dt, that this vector equals lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, times y1, y2, y3. This is what I want. That's what the system of differential equations is. So that's the same thing. If I multiply this out, I have lambda 1, y1 plus 0 plus 0. 0, lambda 2, y2, 0. 0, 0, lambda 3 times y3. So I have lambda 1 times y1, lambda 2 times y2, lambda 3 times y3. So that system of differential equations is the exact same thing as dy1 dt equals lambda 1 times y1, dy2 dt equals lambda 2 times y2, dy3 dt equals lambda 3 times y3. When we were talking about these mixing problems, the rate with which the coffee in the kitchen changed depended on the amount of coffee in the kitchen and the amount of coffee in the lounge. And the rate with which the coffee in the lounge changed depended on the amount of coffee in the kitchen and the amount of coffee in the lounge. We didn't have things so nicely separated because right here, dy1 dt only depends on y1. dy2 dt only depends on y2. dy3 dt only depends on y3. There's no coupling between the unknowns. Why did it turn out so nicely? What's special about the matrix? It's diagonal. So from this, you get that y of t, well, the first component is just dy1 dt equals lambda 1 times y1. We know how to solve that. we just get c1 e to the lambda 1 t. The second component, we're going to get that from the differential equation dy2 dt equals lambda 2 times y2. Its solution is going to be c2 e to the lambda 2t. The third component, y3 of t, we're going to get by solving dy3 dt equals lambda 3y3. And so that is going to be some number, e to the lambda 3t. So step 1, you knew how to do from grade 12. Step 2 is the fact that if you're given a problem, dy dt equals ay, where this is diagonal, then it's something you can do. So this makes you wonder whether you can somehow leverage this. So if you're given dx dt equals a times x, and a is diagonalizable, maybe we can somehow leverage this. Use the fact that at least we can solve it easily when it's a diagonal problem. So we have that dx dt is equal to P inverse AP times x, dP. Right here I used the fact that A is diagonalizable. The fact that I can write A as P inverse D times P. I could multiply on the left-hand side, and I would get P dx dt. Hold on. I got this back. I always get this backwards. This is P inverse. A is diagonalizable means that A is, it means that A is equal to P d P inverse. I'm going to multiply on the left by P inverse, so I have P inverse dx dt is equal to D times P inverse x. I did that because I'm trying to somehow reduce this to a problem like dy dt equals D times y. So there's one step that you need to check at home, which is that this is true. But this is what I'm trying to. That if you have a matrix, that if you have a matrix times a vector and you differentiate it, as long as the matrix entries are independent of time, that you get this. So this is something you can check at home. So we're trying to solve this. So here, this is the closest we can get. Right here we saw that it's easy to solve dy dt equals diagonal times y of t. And here we've rewritten this problem as d dt, this equals diagonal matrix times that. So at this point, you need to have an idea. And you get desperate. You realize that if this weren't that, if this were just y of t, you would be done. So the big idea is to define y of t to be P inverse times x of t. So what we figured out is solving dx dt equals a times x is the same as solving dy dt equals d times y if a is diagonalizable and y of t is equal to p inverse times x of t. So we have a problem that we don't know how to solve, and we've reduced it to a problem that we do know how to solve. Because we do know how to solve dy dt equals a diagonal matrix times y. By step 2, y of t, so we'll just do the 3 by 3 case, is c1 e to the lambda 1 t, c2 e to the lambda 2 t, c3 e to the lambda 3 t. And this is equal to p inverse times x of t. So did I start out asking what is y of t, or did I start out asking what is x of t? I was trying to find x of t, right? Is there some way I can get x of t from this? I know this. I've been so smart, I have figured that out. How can I get my hands on x of t? Multiply by p. So if I multiply by p, I will get x of t. So if I have that y is equal to p inverse x, if I left multiply by p, I have p times y is p times p inverse times x. And p times p inverse is what? Identity. And identity times x is what? X. So I have x of t is equal to p times y of t. P is built out of the eigenvectors v1, v2, v3. Y is c1 e to the lambda 1t, c2 e to the lambda 2t, c3 e to the lambda 3t. And if I write that out, I have x of t is c1 e to the lambda 1t times the first column of p plus c2 e to the lambda 2t times the second column of p plus c3 e to the lambda 3t times the third column of p. So that was, this is if A is 3 by 3 and diagonalizable. So this is an alternate proof of the exact same theorem. If A is a diagonalizable matrix, then you can write down a solution for any, and then there's the general solution. And the fact that you will be able to solve every initial data is because P is invertible. To find the coefficients, we need an initial condition. X at time 0 is C1 V1 plus C2 V2 plus C3 V3, which is P times C, and we want it to be equal to the vector x0. Will I be able to solve this for every x0? that comes down to whether or not P is invertible. Is P invertible? Yes, because A is diagonalizable. Can always solve for C. Because A is invertible, diagonalizable. So what's the recipe? If you have a specific system with specific initial condition, first you find the eigenvalues and the eigenvectors. So someone gives you the matrix corresponding to some coupled masses on springs, or you have a linear system having to do with rooms connected to each other by air vents, or whatever. That boils down to you have dx dt equals ax for some specific matrix A. So you have the specific matrix A, you find its eigenvalues, you find its eigenvectors. If you get n linearly independent eigenvectors, you're happy, because that allows you to write down the general solution. It allows you to solve for the coefficients, and it allows you to then plot the solution, think about the solution, do all sorts of cool things. If A is not diagonalizable, then you wait until your second year when you learn about things called generalized eigenvectors, and you learn how to write down a general solution involving eigenvectors and generalized eigenvectors, and then you solve for the initial data. But for this course, if we give you something like this, that matrix had better be diagonalizable or there's a typo. And if we give you something like this, you can imagine it's a very popular type of question, because for us to ask you to solve, if we ask you to solve dx dt equals 311131113 times x with initial data 1, 2, 9. If we ask you to solve that, we are testing you on eigenvalues, we are testing you on eigenvectors, we are testing you on whether or not you understand that is the general solution, and then to ice the cake, we're asking you to do a problem from chapter 2 of this form when you find the coefficients. So this is sort of a big testing thing, and it's super important. This is not us just because we like math. This is because you are going to need to solve systems of linear equations, whether you're doing circuit analysis, whether you're doing mixing problems, whether you're doing coupled masses on springs, which is a way of modeling materials. If you have to think about when you have a solid material and you deform it a little bit and let go, how it responds, that's going to be a coupled system of linear equations. So are there questions? At the most basic level, you just memorize the algorithm. No questions?